Hello, good afternoon, everybody. Welcome to this IPARCOS colloquium. Our speaker today is Professor Ana Achucarro from Leiden University. And I first met Ana, I think that it was in hold on a second, I'm sorry. Our speaker today is Professor Ana Achucarro from Leiden University. I've got something wrong here, so hold on a second. Okay. Sorry, but I had the volume on or something like that. I was saying that I think that I met Ana Achucarro first time probably in 1989 when I was visiting the Department of Applied Mathematics and Theoretical Physics in Cambridge. Probably it was a party by Stephen Hawking or something, but I remember that she was coming from Imperial College at that time, so it's a long time ago. So she got her PhD thesis in Cambridge under the supervision of Paul Townsend, if I'm correct. And the thesis was about supersymmetric extended objects. This is probably one of the first places in which the concept of branes appeared. And afterwards, she was a postdoc at Imperial College. Then she was also at the University of Basque Country. And then she went to Tufts University. Probably these last two these last two positions were sort of mixed along the years, if I remember also correctly. And then she joined the University of the Basque Country in 1994 as a reader there, and then became full professor of theoretical physics in 1999. And 4 years later, she joined Leiden University as again professor of astrophysics, astroparticle physics, and quantum field theory. Her lines of research cover a variety of topics that are related to supersymmetry, astroparticles, early universe, topological and cosmic defects, inflation, and so on. And probably we will see some of these concepts in the talk today, some of them at least. I don't want to be talking for very long, but I think it is worth mentioning that Ana was also the organizing of the outstanding conference series Science of the Cosmos, Science in the Cosmos, with the emphasis put in the of and in the in the sense of using cosmos both as an object of study and as a way in which you can do physics. This was organized by the BBVA Foundation, and I think she was organizing for 7 years or something. And there was an unparalleled list of speakers that range from Kip Thorne, that I think it was the first one, to Michael Kramer in 2018, that was the last one. And it was, I have to say, because I attended many of them, it was an outstanding conference series. I haven't seen anything like that. So I think it's worth mentioning as far as popular science and trying to make science available to the public is concerned. So without further ado, I will stop here and I will let Ana talk in this IPARCOS colloquium about a topic with the title Observing the Big Bang. So Ana, please.
Thank you, Luis. Thank you for this introduction, and it's been so much fun to do. I mean, certainly to meet with you over the years, and also to see you at the conferences in Madrid, at the talks in Madrid, where we kept trying to guess who was going to get the next Nobel Prize, and actually scored quite a few. So that was very nice. My title today is grand. It's Observing the Big Bang. Oh my God. Okay, and I hope that it's meant to be. You're a difficult audience because you're a very varied audience, and I know that there may be students, and so I'm going to try to give a little bit, maybe a little bit for everybody, which may mean that there's nothing for everyone, but. Let me see if it works. And let me start with the talk. Basically has a preamble and then a postamble, if you want. I didn't call it that, but the title is so grand that I think it needs a little explanation. Now, you all know this image, the Hubble Extreme Deep Field, and I heard this morning from Jesus Gallego that he has spent many years working on it, and that's I mean, what a lucky person he must have been. This is to me, is one of the most beautiful images we have, but I just picked one because it's iconic. But the point of this image is that because light travels at a finite speed, whenever we look through a telescope, we really are looking at it's a sort of time machine, right? And in fact, you could separate the objects between the ones that are. Can you see my cursor, Luis?
Yes, I can.
Okay, good. So there in that image, some objects are reasonably close to us. They may be less than 5 billion years from us. Some objects are further. So then they, as you know, light has to travel further, and we can do a sort of tomography, if you want, or we can sort of unfold the dimension of distance, and the question is, how far can we go? We have a history of the universe where we would be sitting here, and the beginning of the universe is somewhere around here. Something happens, inflation, quantum fluctuations, and then at some point we begin to see light and different types reaching us to today. I mean, time runs from left to right in this picture. Right, and so the question is exactly what I was saying. You know, if I want to go back in time, how far can we go? And the answer, if you're using photons, is clear, because the oldest photons that we can get are the cosmic microwave background, and we know that there cannot be photons. We don't receive any photons from earlier than that, simply because the universe was opaque. There was, it was a plasma. It was so hot that photons couldn't escape. And so it's like trying to look into the sun in some sense. You see the surface of the sun, but you cannot see inside because it's so hot that the photons cannot escape. Let me just point out that this image is a little bit like when you have a map of the Earth. It's meant to be, I receive light from all around me. Luis, can you see my hands, and can you see me?
Yes, yes, okay. I can.
Right. So you could say that this central part would correspond to what's in front of me, and then the two parts behind are here and here, and you've got the whole sphere around us represented there. What can we do beyond that? Well, we've already said with photons we cannot go any further. Oh, let me point out something, because this is interesting actually, and it's going to come back. This is a remarkable thing about the cosmic microwave background, is the fact that it seems to have it's incredibly homogeneous in temperature, no matter where you're receiving the light, and it's 2.7 Kelvin, something like that. But the interesting thing is, if you imagine two photons coming from opposite directions, those two photons have the same temperature, and yet they were never in causal contact. They could have never been thermalized or anything like that, because one of them has been traveling for 13.5 billion years from this direction, and the other one same from here, and the universe is only 13.8 billion years, so they didn't have time to communicate. And this was a puzzle that was it's fantastic, because it tells you that the early universe is very homogeneous, and that means that we can do calculations very, very well. But it's very puzzling from the point of view of how is it possible that I get such homogeneous information from things that never talk to each other, never had time to communicate. And so the idea is today, there's some mechanisms for how this could have happened, and I will be discussing one of them, which is that it's not the only logical possibility, but it's certainly the one that seems to work best. And it's the idea of inflation. And so inflation is simply the idea that you had exponential expansion of the universe, And it's very, very fast. It happens very early, and it basically, the universe expands so fast that it means that the photons from there and from here were sufficiently close to have been in causal contact. Okay, and so I will be talking about this. It's hard to imagine these things, so just to give you some idea of what sort of numbers we're talking about. If you imagine this point here, there are models of inflation where that would expand to something bigger than the observable universe today in a fraction of a second. And see, I mean, it's hard to wrap your head around that, but this is the numbers that we're working with. What can we do beyond with photons? We see nothing, but of course, we know there is a neutrino background. There is probably a gravitational wave background also, stochastic or from inflation or whatever. And those are much weakly coupled, and so they're much more weakly coupled, and so they can go even further back in time. But any hope of detecting those is certainly not. The neutrino background is not going. We're not going to be able to detect it anytime soon. We don't have a technology. The gravitational waves, we might be lucky. LISA, the space antenna, is going to try very hard. We have pulsar timing arrays who are also very busy, and perhaps we have detected some stochastic background of gravitational waves. It's not completely clear yet, but there was a nanograph announcement earlier this year, and so we're watching this space, of course. Well, the point of this talk is that we think we can do much better than that. And the reason why I say we think we can do better and not just we can do better is, of course, because everything I'm going to tell you about inflation is not proven. It looks very reasonable, and there is quite some evidence that it probably is correct, but we don't have the definitive proof yet, and so I can only speculate to some extent. And the reason why I think we can do better, if we go back to the cosmic microwave background, is precisely this is what we're used to seeing it with the fluctuations amplified tremendously, so that you can see them in the diagram. And the fluctuations in temperature are maybe 1 part in 10 to the 5. They're this has been in the newspapers repeatedly, so I don't think I need to explain too much about it. But so here you have points where it's colder. If it's blue, it's colder than the average, and if it's red or yellow, it's warmer than average. And absolutely tiny differences. And the thing that this was done already by WMAP, not even Planck, the previous satellite that studied the cosmic microwave background from space. It turns out that not only the temperature of the photons is correlated, but there's also correlations between these fluctuations that are super causal. They couldn't be causal in a normal history of the universe, and inflation provides also a reason for those correlations. Now, you can imagine the thing about inflation. If you think about what I was telling you about this little point here and the fact that it expands to something like larger than the observable universe. And I said in a fraction of a second. And when I say a fraction of a second, it could be 10 to the minus 32 seconds. I mean, it's absolutely brutal. But in such a fast expansion, such an exponential expansion, even the quantum fluctuations don't have time to react. And so everything, they freeze and they're thrown in the sky. And what is amazing is that here we are so many billions of years later, and we are seeing them almost more or less as they were in the first instant. And so in that respect is what I mean by observing the Big Bang. We can observe something that was happening at the time of the Big Bang, maybe 10 to the minus 32 seconds after the Big Bang, just before we entered the the hot Big Bang era, where the universe is very hot and very dense, and it's expanding and cooling off. And so this is a sort of explanation for why we have these fine-tuned initial conditions for, say, for what we see in the temperature of the cosmic microwave background. But it also is a mechanism where you can explain the primordial perturbations that we observe, and you observe. I mean, so the reason why they're there is they have a quantum origin. Okay, they are in some sense quantum fluctuations. The perturbations that we observe have properties that I have listed here. So superhorizon is this idea that there are correlations that seem to be not causal. They have a power spectrum which is almost scale invariant, and they're also Gaussian and adiabatic. And I think adiabatic is the one that is not usually so clear. So let me just say a couple of words about what it means. If you imagine two parts of the universe, and you have, some photons, some dark matter, some whatever, some curvature, and then you have another part of the universe which has a different curvature and some other content of photons, whatever. And I want to know whether this fluctuation is adiabatic or not. What you need to do is you take one of them and you expand it. Okay, you imagine the universe or the box, expanding the box, and then you look at, okay, so I had matter in there. Okay, so the matter goes down with 1 over the volume. If you have some photons in there, the density of the photons goes not only as 1 over the volume, but there's 1 more power because it also gets redshifted. So it goes like 1 over the size of the box to the 4th power. And maybe I have, some curvature. The curvature also gets diluted. And then if I can do this expansion and then look at this other part that I'm comparing to, and they coincide. In other words, if the difference between them can be corrected by expansion, then this perturbation is called adiabatic. And in a moment, you will see why inflation will give you this automatically. Okay, so what's the simplest idea of inflation that I think is quite popular? And so I'm just going to, I've sort of done it here in 3 very quick pictures. The basic idea is that you have some scalar field that we call the inflaton, and the scalar field has some potential. This is a graph of the potential of the scalar field. And this potential has to be, so the field is somehow rolling down this potential. And because it's up here, this is a sort of vacuum energy for this field. And the vacuum energy is exactly what you need to create, or it can mimic a huge cosmological constant, if you want, in the early universe. And so it produces exponential expansion. Of course, it's not a constant because the field is trying to roll downhill, but because the expansion is so phenomenal, it gives a lot of friction. So when the expansion is very fast, this slows down the fall of the inflaton, if you want. And so this field is evolving slowly, very, very slowly, as if it were sitting in one point without moving. Then we would get, this is the perturbations, the primordial perturbations that you would get. And remember that you're supposed to think that there's some quantum fluctuations, and the quantum fluctuations get expanded and frozen. I will explain. I will show you some formulas for this in a moment. But so if the inflaton were sitting there without moving, then I would get a spectrum of perturbation which would be perfectly horizontal here. Instead, since it's going down slowly, then the spectrum is also losing power slowly. And so you get something that has more power on large scales than on small scales. And that, so it's a slightly red spectrum, which you can characterize by basically the amplitude and how much it differs from the straight line, which is what's the spectral tilt. From the horizontal line, pardon me, not from a. So this would be the power spectrum in momentum space, and then this is three-dimensional, and that's what gets processed into the peaks and all the things that we see in the cosmic microwave background. Right, and the whole point is that this is a really, really elegant and simple explanation, where all you need to know is this function v of phi, which is the potential of the inflaton, and then that is enough to be able to say what this is going to look like, except for the fact that you don't know the amplitude. So the amplitude you cannot predict, and so okay, you don't know what it is. That's all. Oh, I didn't like the look of that. Did you see everything going blue? Because it went blue on my screen. All right, so if this is the case, okay, I'm creating some perturbations here. And again, I will go back and try to explain this in a bit more detail later. The point is that these quantum fluctuations, if you look at the statistics of what I see in the sky, that is derived from the quantum statistics from the quantum processes that were happening at the time of inflation. And we've just said that inflation is even before the hot Big Bang, is in the first fraction of a second. And so it opens the idea, or if recovers the idea, if you want, of thinking of the universe as a particle accelerator, the cosmological collider. Okay. Now, here's an attempt. As you can see, I use a lot of Baumann's figures, which are really, I like them very, very much. And so here's a cosmological collider in the modern version. So what you have on the left would be a normal collider where you have some process, some collisions happening here, and then the products of the collisions are flying over here, and you have your detectors placed on the outside here, and you're looking to detect correlations between the products to be able to say that they come from a particular collision in here. The idea with the cosmological collider is sort of inside out. Here is the Earth we are observing, and we are observing through different methods, or through different collision products, if you want. We are observing something that happened around us. This would be the start of the hot Big Bang. Okay, and something happens before that, or even further than the hot Big Bang, maybe some string theory, whatever, which decays into we don't know what. And so the primordial perturbations here is what what we are seeing the effect of down on the Earth. And so it's a sort of inside out. And just to explain, so CMB is short for cosmic microwave background, which I was just talking about. And of course, the cosmic microwave background then continues. At some point, you start forming large-scale structures like galaxies and clusters and whatever, which is just the result of the same primordial perturbation. If I have an overdensity here, an overdensity, even if it's a very small overdensity, will start collecting products from around it. And so it grows in time. And so after a while, you just have, you start to form galaxies and other things. LSS is short for large scale structure, which is this part here. And gravitational waves, GW, this also there. Okay, so the message is that you have to remember is that all we can observe cosmologically in this cosmological collider is the perturbations created during inflation. So we have no information on the background expansion, on why it expanded so fast or anything, but we do have very precise information about these perturbations that we think are a manifestation of the quantum properties of the fields that were around during inflation. And so what we see on CMB scales are indeed adiabatic, near-scale invariant, almost Gaussian, and acausal. And so inflation gives you in a very natural way, in a very simple and elegant way, the properties of the perturbations that we have seen. So if we are supposed to think, if you want, the more recent way or modern way of thinking about this is, forget about the single field and anything like that. You have two problems that you have to solve, and you can decouple the two problems to some extent. The perturbations you treat, you throw the kitchen sink at the perturbations, the high energy particle physics techniques that you would use in a normal collider. Try to adapt them. It's not very easy at all. But there's some very brave people there who are trying to adapt all these techniques to make them useful for cosmology. And so you are going to be looking at things like, 2-point correlations, 3-point correlations, 4-point correlations in the CMB, in the large structure, so in the distribution of galaxies or anything like that, and so not only do you focus on the endpoints, but then you try to stay agnostic as to what sort of theory could have generated those. And so you use techniques that you use in particle physics, in particular effective field theory or Bootstrap. I will show you in a moment what the Bootstrap is. And the idea is that you are going to try to classify all the possibilities when you're studying these endpoint correlations, these triangles and figures in the sky, and the idea is that you want to classify what there is, and then you also, if possible, you want to find some smoking gun things that can give you information about the physics that you're trying to understand, which is there a new particle? What is its mass? What is its spin? Whatever. Okay. And so the idea of throwing all these particle physics techniques is that, first of all, because it allows you to compare it, you want to do it so that you compare with what you observe, which is the correlations. And second, because you're looking for a very small signal, and so if you can make templates that can extract this signal, then you're helping the detection as well. At this point, I would say, are there any questions? But since we've said that there are no questions, I will just continue. This is just to impress you or me, anyone. This is sort of what these things look like that particle physicists use. For the particle physicists in the audience, this is perhaps a more understandable part. And we are using the fact that inflation has a Goldstone boson for broken time translations. And so the action looks, you can actually write things down for this Goldstone boson with perfectly standard techniques. And here you're doing sort of the same in a slightly different language. But these people, I think what is interesting is to see the year. I mean, this was from 2008. So it hasn't been around that long. Okay. And I also mentioned these bootstrap methods, which again, I'm not going to talk about this at all, but largely because I would not be able to. But in any case, the bootstrap is you go even further and you say, okay, I'm not interested. I don't even completely bypass anything to do with time evolution, equations of motion, whatever you say. There is some physics in here. And all I know about this physics is that it has sort of the fundamental principles of things like localities. I mean, there's no action at a distance in this physics, or unitarity, which is, the quantum mechanical probability is conserved. Symmetries, what symmetries are acting here, whatever. And you go straight from those to the observables that you're trying to write, which in this case is, again, the endpoint correlation functions for these primordial perturbations. And again, so this was started even more recently. So it's not even 3 years ago, and it's really a handful of people who are trying to push this program. And here, what they do, they're assuming that the expansion is perfectly exponential, and so they're using the symmetries of de Sitter space. For those of you who know about de Sitter space, so in some sense this is complementary to the effective field theory approach that I was showing you a minute ago, because the effective field theory approach, in all of these coefficients and things, it can, this is sort of background expansion, and this CS squared is also something that is given by the background, and so all of it can be changing with time, and it allows you to study time-dependent problems as well. So, okay, well, so this is, let's say, the perturbation part of inflation. And in the simplest models that have been around since the 80s, usually you have one quantum field, which is, you call it the inflaton, and that is responsible for both the background expansion, as I was explaining, rolling down this hill, and also the perturbations. And so nowadays you think of it more like a toy model, because the situation presumably is more complicated, and we don't know what the inflaton is, but for a start, at least now it could be, we know of at least one scalar field in nature, which is the Higgs. And so maybe that scalar field before the hot Big Bang is also responsible for inflation, in which case we would know what the field is. There are other possibilities. I mean, here is just it's some quantum properties of just gravity, which act as if it were a scalar field. But it could also be that the inflaton is just something which is not in the standard model at all. And so it's either a new fundamental field, or maybe it's some effective field where you have some complicated situation and you've integrated out some heavy degrees of freedom, and you end up with some effective theory where there's this degree of freedom, which you call the inflaton. And the third possibility is that it may be that it's not just a single field driving inflation, but there's more than one, and then it's a multi-field inflation. And but whatever it is, we know that the standard model of particle physics is not enough. Okay, so the standard model is incomplete, is fantastic, but it's incomplete because it doesn't have a dark matter particle. It doesn't have a way to give neutrinos a mass, and it doesn't explain the matter-antimatter asymmetry. So we know for sure it's not the end of the story. And now here we have something else that has to be explained, which is this inflaton, or this mechanism for inflation. And what you want is you want some theory that includes the standard model, that explains inflation, and that can go all the way to include quantum gravity effects and everything you might need. Okay. The point here is that it's very important that the techniques that you use are agnostic about this new physics that you're looking for, and that's why the entrance of effective field theory methods has been so interesting in inflation. Couple of examples that, Occam's razor, what would be the simplest model that explains cosmology? Well, here's one. It's not completely dead yet. And it's so basically you take the standard model, you add 3 neutrinos. The 3 neutrinos, if you add them carefully, this is Shaposhnikov's work. If you add them with the right masses and the right couplings, they can give masses to the neutrinos, and you can also get a dark matter particle. And then the question is, okay, so I've solved that part. You can solve the baryon asymmetry. You can everything that you already know is there. And then the question is, where do I get inflation? And so there's a way to do inflation with the Higgs. And what is very tantalizing is that there was an observation in, I think, 2014, something like that, these two groups that reported a 3.5 KeV line, and that would be consistent with the 7 keV neutrino, extra neutrinos, one of the ones that you've added, which could be a dark matter, a candidate for dark matter. It's a very different type of dark matter from usual. And so the discussion goes back and forth, and okay, as far as I know, it's not dead. There's been some more ammunition against it, but it's really not dead. It would be a very interesting possibility, because then this model would be valid all the way to the Planck mass, and then something else takes over. We don't know what, but basically everything we see is explained. The other opposite, if you want, is that we have just one field with a potential, the simplest thing you can write, which is these are called chaotic inflation models, but it doesn't matter. You just have a field that's is displaced and rolling down to its minimum, and so it's a slightly different technically, but it doesn't matter. It would have to be that scale, and these were the models that BICEP 2 would have proved if the result had been correct. And of course, we know that it wasn't. So this is under pressure from the observations. So probably it's not what it was. But I will revisit this idea a little bit later. So let me just leave it there. If you look at that model at face value, it would be these points here. So I mean, it's really not well. This was the Planck 2015 data, and the Planck 2018 data even more constrained would be here. So it doesn't look very good. And maybe, sorry, yes, no, that's fine. So I will explain something later. And the other interesting thing about these simplest models of inflation with one field is that lately there has been pressure from a very interesting corner, which goes under the name of the swampland discussion, and I'm sure your theorists are well aware of this, which is if you look at what field theories we can write, let's say 4-dimensional, here you have them, 4-dimensional models, theories that you can write, which are of the type of that we use for the standard model, but coupled to gravity. And you ask yourself the question, which theories are actually descending from a proper theory of quantum gravity? And it turns out that it's not free for all. So the string compactifications or quantum gravity theories land on a particular subset of theories. It's not even, this is again another industry now in string theory. There's so many papers back and forth trying to understand exactly what are the conditions, what can I write down, and what is not descendant from it, what doesn't have a proper ultraviolet completion in a good theory, and those are the ones that fall in the swampland. And so it's been called the swampland debate, the swampland constraints, the swampland discussion. And it's basically the idea of how do we distinguish theories that have a good quantum gravity completion from the ones that don't. And it turns out that inflation in the simplest models, where you have a single field creating both the background expansion and the perturbations, are under pressure here, simply because the conditions, one of the conditions to be in the landscape and not in the swampland is that the potentials have to be steep. And so steep potentials are not good for inflation. We said we needed flat potentials, and somehow this appears to be a problem. I'm not going to say more about this, but just so you know that all this discussion is interesting. And it also is interesting that the pressure that these swampland conditions are put on the simplest models, they don't hold so much for when there's more fields around. And so the moment you say, okay, this was a toy model and what I really need to solve is a problem with many fields, then all of these constraints can be evaded. And so again, all of that is under discussion, but it's interesting. All right. So basically, I mean, I could have ended the talk here in some sense. And if I look at the time, okay. So what I would like to do is simply to give a little bit more detail about how inflation creates the primordial perturbations, and so how can we exploit the primordial perturbations to try to learn something about fundamental physics at the beginning of the universe, really. So how can we observe the Big Bang? And so what I'm going to do, I'm not going to do any of the, I've already shown you all the flashy, complicated things, but I'm going to try to explain a bit more about how inflation generates the primordial perturbations, and also about what is the difference between having, say, more fields, or what you have to watch for. And here it is again. Inflation is something that has very nice properties when it comes to explaining the universe as we see it. And of course, inflation was proposed because it got rid of the monopole problem. So any relic, any massive thing that's lying around, you sort of blow it out of the observable universe, and so that's it. You don't have a problem with massive relics anymore. It solves the horizon problem. That's what I was explaining about the fact that the photons are too similar between parts of a universe that were never in contact without inflation. And the flatness problem is okay. It's simply the idea that the universe looks too flat if you just think of how Einstein gravity. In Einstein gravity, the curvature would grow with time to the point where it couldn't be as flat as it is now. I mean, it would have to be very, very flat initially, but inflation does this automatically, because if you have some curvature and you inflate, the curvature, of course, goes down. But besides the fact that inflation does all of these good things, the most important thing is that inflation gives us a mechanism to generate the primordial perturbation. And it's a very physical, nice, natural mechanism. And so that's what I want to focus on. Now, the quantum fluctuations of any field that's around will generate these inhomogeneities. If the field is massless, we will see them there today. And so in particular, the gravitational field is massless. And so inflation will also produce, or did also produce, if it happened, it produced a background of gravitational waves. And that's the one that we haven't detected yet, the primordial background. The only way to see it is in the cosmic microwave background in the polarization, because so what this gravitational wave background, what it is really quadrupolar distortions, and the quadrupolar distortions affect the polarization of the photons in the CMB. And that's what BICEP 2 thought they had seen, but then turned out that it was just some foreground, and we haven't seen anything. It's going to be a target of the next generation of cosmic microwave background experiments, because, I mean, any detection of this background would be amazing, because it would confirm inflation, it would confirm the quantum nature of the gravitational field, and it would be fantastic. So let's just go back to Baumann's lectures again. And here's an explanation. This explanation is actually really, this way of thinking is really due to Hawking, in fact. So here's a potential, okay, and the idea is that here this would be the inflaton, and the inflaton is evolving as a function of time. It's rolling down the hill. It could be coming from here, or here's another example where the inflaton might be up here and it might be rolling down if it's a slightly different type of inflation. So this would be the chaotic that we were talking about before. This is, and so how do we think about how the density perturbations are generated from quantum fluctuations? Okay, so this is the potential, and so if I have fluctuations of this inflaton back and forth, all that happens is that, so suppose that you have in some part of the universe, the inflaton is here, in some other part of the universe, the inflaton is there. Well, okay, so the one that where the part of the universe where the inflaton is here is ahead in the sense that, inflation is going to end earlier. Now, I just realized that I didn't explain earlier how inflation ends. So you go down, all of this time the expansion is almost exponential. So it's really very accelerated, and as the inflaton begins to roll down, and also the friction becomes less, so it starts going faster. The moment it goes faster, then it stops behaving like a cosmological constant, and now you sort of go into a what is called reheating, which is the inflaton goes back and forth and it decays the idea is that it decays into the particles of the standard model. And so that's the start of here is where the start of the hot Big Bang would be. Okay. And it doesn't matter if I come from here or from there, same story. But the point is that the parts of a universe where the fluctuation, there are some parts of a universe where the fluctuation will make them end inflation early, and other parts of the universe that will take a little longer to end inflation. And so you will have patches of the universe that have expanded more time or less time. And so that's just how you see the differences in density. So in other words, the vacuum fluctuations that spread the inflaton vacuum expectation value, so it's this thing here, turn into, or you can think of them as a local time delay for when inflation ends. And then that local time delay, because it has expanded more or less, you can translate into density fluctuations. And of course, the density fluctuations you see in the cosmic microwave background as cosmic microwave background anisotropies in the temperature. And so the summary is that the inflaton acts like a clock, if you want. You can think of the inflaton as a way to keep time. Okay, so that's idea number one. And idea number two is that we need to look at what do the fluctuation equations look like in an expanding universe. And so basically the fluctuations are, if you ignore this term, the fluctuations would be like a simple harmonic oscillator. And the expansion of the universe, this is with Hubble in here, the expansion of the universe gives you friction. Okay. Now, this during inflation, the Hubble parameter, the expansion is, you can think of almost exponential. So h, which is a dot over a, is constant. And so the question is, look at these two terms. And so we see very different behavior depending on whether this term, so depending on whether k is large, k is the momentum, whether the momentum is in Fourier space is large or small. So if k is very large, then you can basically ignore friction, and then you have simply you have a harmonic oscillator. And so this is the idea here, that is something going back and forth. But if k is small, then this term, so this term is not important, this term would dominate, and so you have a lot of friction. And we talk about this as being inside the horizon or outside the horizon. In fact, the correct way would be to say that large k is either super Hubble or sub Hubble, meaning larger or small compared to this scale. And but let's use the. I mean, this is how it's very often talked about. So we'll keep that idea. And what you see is that the fluctuations go, so that the transition between these two behaviors happens when these two terms are similar. So roughly speaking, when k divided by a, this is approximately h. And so there's some, at some point when Hubble is like this. But of course, a is growing exponentially. So this is becoming smaller and smaller and smaller. And it doesn't matter whether k is large or small. Eventually, you're gonna freeze out. So suppose if you're a large scale, then a large scale means that you have small value of k, and so it means that you will very quickly freeze. So you start like this, and then you catch up with h catches up, and you freeze wherever you were. Okay, and then there's another perturbation that's doing something else, and then it gets frozen somewhere else, and in that way you are generating the primordial perturbations, with the property that the largest scales are going to freeze first because they are the ones that have small k, and so they are already very early on, they are dominated by friction. And so those scales freeze, and then they stay frozen pretty much until today, or until, well, not until today, but until recently, shall we say. And then if you take a slightly smaller scale, that one will freeze a bit later and will also thaw later, earlier than the largest scales. So here, the idea that after inflation they thaw last is simply the idea that after inflation, so you're comparing k with a times h, and a times h is growing exponentially during inflation. And during normal cosmological evolution, you would have, I don't know, if it's matter dominated, you would say this goes like t to the 2/3, and this is 1 over t, and so the combination is always going down. So in normal cosmology, in post-Big Bang cosmology, then the combination AH is going smaller and smaller, and so you have sort of the mirror image of the effect that we were seeing here, which is that the largest scales freeze first, and on the other side they thaw last. And the final step is that, okay, we were talking about fluctuations in the scalar field, but we already saw that we can trade those for fluctuations in the density, in the curvature, and so the interesting thing about this particular curvature is that this is conserved on superhorizon scale. So once the fluctuation leaves the horizon, it stays with exactly the same value past, the end of inflation and everything that happens in the Big Bang era until much later, when they start again oscillating, and those are the ones that you see, for instance, in the cosmic microwave background. Right. So a few words. What I want to do now is to remember that I mentioned the m squared phi squared. So I want to introduce, I know I have to have an action in there somewhere. So this is the action for a single scalar field. Here is the action for gravity. This is Einstein-Hilbert. This would be simply the usual d mu phi in Minkowski space, but the only thing is, instead of Minkowski, you have an expanding universe. So you're going to have this. This is the background space-time metric. Single field. That's all. This is my scalar. All I'm doing is I'm putting it in the universe, in a cosmological expanding background. And this is the famous potential that we've been looking at. Now, this is called canonical kinetic terms for the high energy physicists who know this. I don't need to say it. The other thing is that we are going to assume that the vacuum for the fluctuation is basically Minkowski on the shortest scales, And so if I do that, then I can follow this whole procedure, and then everything that I was saying is working fine. Slow roll. Well, so slow roll is simply the statement that it's not perfectly exponential expansion. The exactly exponential expansion is what is called a de Sitter spacetime, and here and that would be the case if h were constant, the Hubble parameter were constant. But here instead, what we are saying is that the change in the Hubble parameter is very small in a Hubble time compared to Hubble. In other words, if I have a particular rate of expansion, then the time scale associated with that rate of expansion, h, would be 1 over h. And so I'm asking the question, in a time 1 over h, how much is the relative change in h? In other words, so delta h divided by h, and delta h is, of course, h dot times the time, that's 1 over h, and the final 1 over h. So this is just one way to measure how close you are to perfect exponential expansion. And the slow roll condition is that you should be very close. This combination has to be much less than 1. And you also need that to be sustained for at least 50 or 60 e-folds of expansion if you want to solve the horizon problem and the flatness problem. And so that means that it's not enough for this number to be very small, but it has to be very small for a very long time. And so basically that translates into the idea that it cannot change too much in a Hubble time. And so this number also has to be much less than 1. And all it means is that the universe is expanding, and the changes are such that there's no big changes. In other words, you could say the evolution is adiabatic, just it's almost perfectly exponential. And so this defines single field slow roll inflation for people who know what I'm talking about. And okay, and those types of models are the models that were I mean, this plot from Planck that I was showing, this is simply a whole bunch of potentials and models of inflation against the measurements from studying the cosmic microwave background anisotropies with Planck, with the satellite. And what you have here, this R is called a tensor to scalar ratio. And simply the idea that because it's the same mechanism that's creating the perturbations, I already told you that we have there are 2 quantum fields around that are creating perturbations. One is phi, the inflaton, and the other one is the gravitational field. And because they are in the same expanding universe, their amplitudes are related, and so you can predict what the relation is going to be, and it's related to this slow roll parameter. And that's it. I mean, that's a prediction of these models of single field inflation. And what you have, you plot that against. Remember that I said ns minus 1 is the deviation from a perfectly scale invariant spectrum. So that red line that we had before, that was a little bit tilted. This is the tilt. And again, you can predict, you can relate that to how much the inflaton is, the expansion is changing from purely exponential. These guys here, you see that they have a V and an eta. These are very popular ways to measure slow roll. But these only work when you're in the toy in the simplest models that I was just describing. The moment life gets a little bit more complicated, these parameters don't help, and you have to use these ones that I was talking about, this epsilon and this. So those are the ones that really generalize to any situation. And a little translation for those of you who have seen inflation before and have seen these epsilon and these etas, the slow roll parameters. Historically, these were introduced. I think they may have been introduced even before these ones. I'm not sure. But the translation, here you have it. So these are the 2 that I had introduced. is basically the deviations from perfect exponential expansion. The equations tell you that it's the epsilon parameter is related to the speed at which the inflaton is moving down the hill. And so you can relate, so of course, how fast it's moving depends on the potential, so you can relate them. And to lowest order, when these two are very small, then they look something like this. So the epsilons coincide, and the etas, so the rate of change of epsilon, are related like that. So the observational predictions, I can write them either in terms of the vanilla, the potential, the epsilon and eta derived from the potential, these two. And by the way, what you can see is that epsilon is related to the slope of the potential, and the rate of change of that is related to the second derivative of the potential, which is also related to the mass of the inflaton. So yes, so I have this, and then I can do a similar thing for the tensor perturbation, for the gravitational field perturbations, and then the tilt, instead of ns-1, is just called nt for tensor. And you can see that in the simplest models, it is related to this tensor to scalar ratio. I mean, it's basically ways of saying, the gravitational field, the amplitude and of the perturbations is always governed by the same rate of expansion, and so therefore they are related. Right. So this was the Planck 2018 that I showed before. And so what I want to do now is take the model that we were looking at, and now I want to do the multi-field version, which is a cartoon example. And I have to say, oh, yes, I just looked at my watch and I realized that I shouldn't be much longer. Okay, so this is I can go reasonably fast through this, because this is specifically for the particle physicists, and it's an interesting message for people who are interested in inflation. So what I'm going to do is the following. I'm going to take this phi squared potential that I had before, and I'm simply going to say, okay, instead of being a single field, I have two fields. I have a two-field model where the inflaton is there because of some symmetry, and there's a second field which is very heavy. And because it's very heavy, I'm going to integrate out the heavy field, and then I know that the action I get should be the single field action, so I'm fine. And then I'm going to do the analysis. Let me just, this is what it looks like when it is really a single field, nothing else. And so what I want to do is just to look at what is the simplest two-field completion that I can do. And so imagine the inflaton is the face of a complex field. So it's like a Mexican hat or something like that, right? And so what I do is I say, okay, the radial part of this field is extremely heavy, and it's going to be stabilized as at its vacuum. And then I have this field, which is the phase around the rim of the Mexican hat, if you want, which I can think of as a Goldstone boson. It cannot be perfectly flat because I need to inflate. So it's okay. So that symmetry is a little bit broken. And so what do I write down? I simply write down an action, which is the Einstein action plus, and now what I have, my basic field is this, and I want a U1 symmetry. I am accelerating on purpose because whoever knows what I'm talking about knows what I'm talking about. And so this is now a complex field and a potential, which is basically depends only on the modulus of the field, and maybe some terms to make sure that I tilt the rim a little bit so that there's inflation. And so, I should recover single field slow roll inflation again. So here's what it looks like. I have my action, just the fields part is Einstein plus this, and I have the radial part, canonical. Then I have the part to do with the phase, which has this here. And now I'm going to just say, okay, the heavy field is going to be so massive as you want, much higher, much larger than H, much larger than whatever. I give it a mass term like this so that it flows to its vacuum, which is rho 0. And then this is the bit that I have added to be able to inflate in the rim. So let's give it some quadratic just to compare to the previous one. Right? Now, the usual argument goes like this. If the mass is so heavy, then rho will go to rho 0, which means that this term here will not contribute because rho is constant. This term here will become something like this, rho 0 squared times this, and this potential is still there. And now I recognize that this is single field inflation. All I need to do is turn this into a canonical field by a redefinition like this. I introduce phi, which gets rid of this rho 0 squared. So now I have d phi, which is what I had to begin with. And the mass of this field, you can just see what it is. If I replace this by phi, then this gets divided by rho 0 squared. And so you would say, okay, so this is, I will be here. This is the prediction. But it turns out that instead, if you do the problem properly and you look at what the inflationary predictions for this model are, they depend on the value of rho 0. So depending on whether rho 0 is larger or smaller, you end up in here, or you start going down this diagram in the Planck data and entering the region where you are consistent with the data. And so all of a sudden, simply because this second field is there, it turns out that the predictions are different and they are now looking compatible with what Planck sees. And so what happened? What went wrong? And so what went wrong is that we ignored here that there is a derivative coupling in this term. And so the toy models of single field inflation don't have this derivative coupling, but as soon as you go multi-field, this derivative coupling plays a very important role. And if I translate that into a different language, if you imagine that your inflationary trajectory is now somewhere in a two-field space, what you can show is that every time you take a turn, something happens which is different from your naive single-field inflation prediction. So the radius of curvature, the turning rate is important. Not only that, also if you live in a space which is hyperbolic, for instance, all the curvature effects of that space are also important in predicting what the inflationary perturbations are going to look like. So, okay, another way to say is that to go from here to here, like we did, is an inconsistent truncation. And what we should have done is integrate out the field. And then if we had integrated out the field properly, we would have discovered that integrating out the heavy field, the rho field, produces a change in the dispersion relation of the light field. And so it changes the speed of sound of this field. And with the speed of sound, we go down in the diagram. So now, as I was just saying, and I'm going quickly now, so if the mass is really, really heavy, I can integrate the heavy field, I can integrate it out, but the price is that I get a reduced speed of sound. And the reduced speed of sound changes the perturbations. The other interesting thing is that you imagine a situation where you are going, where you're turning, maybe you're straight for a while, then turning, then doing something, then turn. Every time that you turn, you're affecting the speed of sound of the inflaton. And every time you do that, something happens in the power spectrum. And so this is a very simple example. So the speed of sound can be time dependent. You could have a speed of sound that goes from the speed of light, gets reduced by 4% and goes back, which is something that happens if you go around a turn in field space. The effect of this is that this was the red line that we had for the power spectrum. Instead of being straight, starts fluctuating for a while. It has some sort of localized set of fluctuations, of oscillations, sorry. And that translates into a power spectrum for Planck, which actually goes and it can give you a good fit. Now, it's never a good fit. I mean, if you can find because you need more information here, so you've introduced the speed of sound and the change in the speed of sound. Here it was a Gaussian, so you have to give me the amplitude, the position, the width. So I'm introducing 3 new parameters, and of course, you can fit things better with 3 new parameters, but that doesn't mean that they're significant. What is interesting here is that because this reduction in the speed of sound is primordial, is something that's happening really at the very beginning, it's affecting the perturbations themselves. And I am seeing its effect on the 2-point correlation of those perturbations. It has to be there also, it has to be there also in the 3-point function, in the 4-point function, and then all the endpoint correlations. They have to show the effect of this thing on there. And what you see in this case, this is a bispectrum, and the bispectrum also has some oscillations. And this is interesting because Planck did a search for oscillatory features of this kind, but this is one case that they never checked. And so here's one, it's completely well motivated from the primordial point of view, but it has not been looked for in the data as such. And so this, I just leave you with this as a nice example of what it is that you can do when you understand a little bit better what multifield inflation can do. Immediately you see how you have to attack the data in order to be able to detect such effects. And so you would have to correlate what's happening in the bispectrum with what's happening in the power spectrum. And so, of course, this hasn't been done yet, but it's an interesting thing to dream about. And so this is it. Inflation in one slide. I'm not going to repeat it because we're out of time. And in any case, this is being recorded, so you will watch it whenever you want. And I leave you with this much nicer thought, which is that, okay, WMAP and Planck are no longer there, but Euclid is going to study all of this, the distribution of matter in the sky. It's gonna map half of the sky, and it's going next year, so that's fantastic. And LISA, well, it's too early to say when it will be launched, but it's such an amazing experiment, and I'm very much looking forward to it. I may be retired by then, but I think this is it.
So thank you, Anna, very much for a very nice talk. So we have now time for questions. I think we have to wait for a few seconds so that the YouTube channel sort of updates. Okay, in the meantime, I think I can ask you a question so that people start asking their own questions. And the first one is kind of simple in some sense, and it is that perhaps you can tell us a little bit about what can we expect to learn from gravitational wave astronomy concerning the early universe, and in particular about the inflation paradigm.
So there's a lot. So for a start, you have to distinguish between the gravitational waves that are created as fluctuations during inflation, and those. I mean, that is all of that constitutes a spectrum of the stochastic spectrum. But whether we will be able to see those or not, probably not. But there's also other things that you can also see. So, for instance, the scalar perturbations also generate gravitational waves, and so again, things like it's always in the stochastic. Well, I'm talking about the stochastic backgrounds. Another thing that you could have is perhaps if somewhere around here before you generate a network of relics like cosmic strings or something like that, those also generate a background of gravitational waves. If you have the electroweak phase transition, which we don't know how it happens, but if it happens that it is violent, so that it is a first order phase transition, and you start creating, you do it by bubble nucleation, then again, that's also generated various backgrounds. First of all, because of the bubbles, but also the sounds, the sort of the noise from the it also creates more gravitational waves. And so it's going to be the name of the game is going to have to be to cross-correlate whatever you see in gravitational waves with what you're seeing in other instruments.
Okay.
So it's
thank you. So we've got a question in the chat. Thank you for your nice talk. What is the relation between inflation and late-time accelerated expansion? Is there a relation at all?
So in the equations, we don't know. It could be that the inflaton it inflates, and then instead of disappearing completely, that it has a tiny cosmological constant later on, because it's a question of the height of the potential. Right? But there's nothing very clear that you can say. Most of the time you treat them as separate, but of course you would like to incorporate also the cosmological constant or the late time acceleration in the problem. And
Okay, so we've got another question, and it is, how would you qualify the current status of the inflation model? And you have three options: well-defined, stable, or highly speculative.
Well-defined, stable, highly speculative. Okay, so the idea of the accelerated expansion or exponential expansion as the way to generate the perturbations, I wouldn't say highly speculative. I think it's difficult to find. I mean, the properties, these sort of the violation of causality, if you want, in the perturbations, which is very well measured. It was very clearly demonstrated already in WMAP. There is not so many ways that you can explain that. So I would say inflation is the el mal menor. How do you say? It's the least offensive thing that you can do, in some sense. What were the other two? Sorry, I forget. So
well-defined, stable, or highly speculative?
Stable. I don't know what stable means, but yes, it is stable in the sense that it's been bashed badly lately, certainly for all the swampland constraints and things like that. But somehow it finds a way. It finds a way around. And well.
Okay, so actually I have a question that was very related to this one, and it is whether do we really need inflation, or are there any other models that could do the same trick and actually match, of course, observational data?
Match observations. So the problem is with match observations. Yes, there are.
We're doing physics, right? So we should do that.
Yeah. No, so that's the thing. So the problem is that the observations are getting so good that they are ruling out a lot of other options. And okay, so there's the logical possibility that instead of expanding, you're sort of contracting in a decelerated way, and then you go through a bounce. That becomes difficult to do not in a forced way, if you want. So inflation really is what happens. I mean, the moment you throw some fields around, before you know it, they're inflated. So, and we know we have those fields have to be there, right? Some fields have to be there. So it's not, in my opinion, it's sort of it's a good explanation. Of course, if we were to detect the background of gravitational waves, then it would be hard to. Then I think even skeptics would be would be much happier with it.
Okay, I don't see any other question in the talk, in the chat, I'm sorry.
Yeah. No,
So,
the other thing I was going to say is that, we don't know much about quantum gravity, but we know it's playing a role. So,
actually, that was my next question.
maybe it's something different. But even if it's something different, I think at low energy it probably would match. I don't know. I think the answer is I don't know. I should have answered I don't know to all your questions from the beginning. That's an honest.
So probably this is another I don't know, but to what extent do the perturbation seeds have to be quantum? Can they be classical? Or in other words, can we really check the quantum nature of the correlations? So if not, why do we say quantum?
That's the thing. Okay, so again, if you can, well, okay, can we check? Maybe we should take this offline because that for sure I don't know. But yeah.
Okay. So if there are no further questions, so I don't see any other questions.
I'm sorry. No, I was going to say that my talk was 15 minutes longer than it was meant to be. So I mean, I
think that's okay.
I'm surprised that there's anybody still there. So my apologies to everyone.
So thank you, Anna, for a very interesting talk. And of course, you all for attending this colloquium. I'm sure I will see you in future talks, but I hope that they will be in person soon so we can see the faces and not only the faces on the screen. Yeah. So thank you all very much for being here today.
Thank you.